How do isochoric processes generate immense pressure in explosions? Imagine a sealed container filled with gas. Now, think about what happens when a chemical reaction suddenly releases a lot of heat inside that container. The volume stays the same because the container is rigid and cannot expand. This is the essence of an isochoric process. In thermodynamics, an isochoric process is one where the volume of a system remains constant while other properties like pressure and temperature can change. When a chemical reaction occurs in a confined space, like inside a sealed chamber, the gas produced cannot escape or expand. Instead, the heat from the reaction raises the temperature of the gas very quickly. According to the ideal gas law, which states that pressure times volume equals the number of gas particles times the gas constant times temperature, if the volume is fixed and the number of particles stays the same, then increasing the temperature causes the pressure to go up proportionally. So, in an explosion, the rapid releases of heat causes the temperature of the gases inside the confined space to spike. Because the volume cannot change, the pressure builds up very fast. This sudden pressure increase is what causes the container or surrounding material to rupture or explode. No work is done by the gas during this process because work involves changing volume, which is not happening here. Instead, all the energy from the heat goes into raising the internal energy of the gas, which results in the immense pressure. This is why explosions in sealed spaces can be so powerful. The gases produced from the chemical reaction are confined, and their temperature skyrockets. The pressure then reaches such high levels that the container cannot hold it anymore, leading to a violent rupture. This principle is also seen in engines like the Otto cycle, where fuel burns in a nearly fixed volume, causing a sharp rise in pressure that moves the engine pistons. Understanding how isochoric processes work helps explain why confined explosions generate such intense pressure. When the volume is fixed, any heat added causes the pressure to increase dramatically. This is a simple but powerful idea that explains many phenomena involving gases and phase changes, especially in explosive situations.